Hello students, today we will start chapter number 6, that is named as work energy power. I think all of you complete this chapter. There is work energy power, some portion which is in your class 9 and 10. So this class is the first lecture from work energy power, and in this lecture we will discuss about work. What is work? Types of work, that is when work is positive, when work is negative, when work done is 0. And we will solve how to find out work done when a constant force applied on a body, how to find out work done when a variable force act on a body, and then we will solve some basic numericals related to work done. So this is our today class. So write the definition of work. I think all of you know what is the meaning of work. In actual, you are doing something, that means you are doing some amount of work, but in physics there is an appropriate definition of work. There is a condition when work done is 0. So what is the definition of work done? You see, when a work done is said to be, work is said to be done when a force applied on a body and the body is cover some distance. Force applied, and by applying force the body covers some distance along in the direction of force. This is the definition of work. Now what is the mathematical form of work? Write it. That is work done, W, that is equal to the dot product of force and displacement. I think all of you know this dot product. We already completed a vector chapter. The dot product of force and displacement is named as work done. So what is the formula of dot product? F dot S. That means here you can write F is cos theta. So what is cos theta? Theta is the angle between force and displacement, right? Here theta is the angle between force and displacement. Suppose body is placed here of mass m. You are applying a force capital F along this direction, force applied along this direction, and by applying force the body displaced along this direction. Suppose after some time this is the position, new position of this body. So the displacement, this is the displacement S, and this is the value of the direction of force along that direction. So this angle is known as angle of theta. So you know the dot product of two vectors always gives a scalar quantity. So work done is a scalar quantity, and the general formula for finding work done, that is F dot S, and theta is the angle between F and S. Now you see another part, that is if F is directed along this direction, you can divide this F in component form, and this component will be which value? Obviously this is the horizontal component, F cos theta, and this component will be named as F sin theta. So if I say work done W, that is equal to the component of force in the direction of S into displacement, that is also the definition of work done. Actually work done means the displacement multiple of the component of force. Which component? The component which is along the direction of displacement. Here you see F is directed in that direction, so this component is F cos theta. So if we multiply S with F cos theta, that is F is cos theta, and this F is cos theta gives the amount of work done. Okay, so this is the formula, general formula of work done. Okay, now with the help of this formula you can find out unit, dimension of work done. Okay, find it. So what is the SI unit? SI unit, unit of force, that is Newton, and unit of displacement, that is meter. So Newton meter SI unit, which is named as Joule. Suppose you have to define the work done of 1 Joule. Define 1 Joule work. What will be the definition? You see, 1 joule, that means 1 Newton into 1 meter. So the definition will be, right, 1 joule work is said to be done when a force of how much? When a force of 1 Newton is applied on a body and for which the body is displaced. How much? You see, the body is displaced through a distance of 1 meter in its own direction, then this is named as 1 joule. So you always give the definition with the help of this equation. 1 joule work is said to be done when 1 Newton force applied on a body and the body displaced through a distance of 1 meter. Okay, now what is the Cgs unit, right? So Cgs unit, for Cgs unit, unit of force, that is dyne, and the unit of distance, that is centimeter. So dyne centimeter, which is named as arc. So arc is the Cgs unit. So same way, what is the definition of 1 arc work? 1 arc work is said to be done when a force of 1 dyne applied on a body and the body displaced through a distance of 1 centimeter. Now find out the dimension. I think all of you know, that is W is equal to Fs. Now the dimension F, that is MLT minus 2. I think this part is clear to all of you. We already completed dimension, that is unit and measurement chapter, and S, that is L. So this one will be M, C, L and L, that is L square T to the power minus of 2. So this is the dimension of work done. And students, this unit, that is joule and hour, it is known as the absolute unit of work. There is another unit of work which is named as gravitational unit of work, and gravitational unit of work, the SI is named, that is kilogram meter. And you know the relation, 1 kilogram meter, that is equal to 9.8 joule, and 1 gram meter, that is equal to 980 arc. This is the relation. Okay, so this is all about the basic part of work done. Now we will discuss the types of work, when work will be positive, when work will be negative, and when work will be 0. Okay, write it. So now next part, that is we have to discuss type of works. So you know the general formula, that is W equal to Fs cos theta. Types of work done. First condition, suppose if theta is equal to 0 degree, you see theta 0, that means suppose this body of mass m and force applied and the body displaced along the same direction. So this is the displacement, force applied and the displacement of body is along the direction of force. So here the angle between force and displacement, that is theta is equal to 0 degree, and when theta is equal to 0 degree, you know the formula. So F will be Fs cos 0, and the value of cos 0, that is 1. So work done W equal to F into S. This work done is known as positive work. This is named as positive work. You can write this value also. If theta is less than 90 degree, that is the angle is named as acute angle, and less than 90 degree, that means cos 90 value, that is 0, and so less than 90, that is positive. So when the angle is less than 90, in that condition work done W will be positive also. So when theta is equal to acute, the amount of work done, that is positive, and this is happens, that means the logic, that is force is along the direction of displacement. So what is the example of it? What is the example? You see, a freely falling body, a body is falling freely. So the gravitational force directed downward, and the displacement of body, that is also downward. So both are in the same direction. So here theta is equal to 0 degree. So a freely falling body, the work done by gravitational force in case of a freely falling body, that is positive work. Now another point, suppose case 2, if theta is equal to 180 degree, 180 degree, that means suppose body of mass m, you are applying force in this direction, but the body displays in this direction, opposite direction of force. Force applied positive x-axis and the body displays along negative x-axis. So angle 180, and you know the formula, so result will be Fs cos 180. Cos 180, that is minus 1. So this value will be minus Fs. This work done is named as negative work. This work done is named as negative work. So what is the example of negative work? And you see, in this condition, theta is greater than 90 degree. Theta 90, that is 0 value. Theta when more than 90, cos value that is more than 90 is gives the negative value. So in that condition, the work done is negative. So here you can write this angle, that is obtuse angle. So when theta is equal to more than 90, that's the angle is obtuse angle, and this value is named as the work done is give the negative work. Now what is negative work? What is the example of negative work? You see, a body is moving upward, but acceleration due to gravitational force is directed vertically downward, and the body displays upward. So the displacement of the body upward, but the gravity directed downward. So here the work done due to this gravitational force is negative. Yes, is negative. And what is the meaning of this negative and positive work? The meaning of positive work, that means you are supplying some energy to a body. When you are supplying a force in that body, the body attains a velocity. The body increases velocity, and velocity increases, that means its kinetic energy increases. Kinetic energy is form of work done, is form of energy. So positive work, that means you are supplying some energy to the system, to the body. And negative work done, that means suppose you are applying force along this direction and the body is going like this way slowly, because you are absorbing this amount of energy taken from the system. Energy work done negative, that means you are taking energy, and work done positive, that means you are giving energy. Okay, now another condition, that is when the work done is 0. One condition is, that is you are applying force but displacement 0. Force applied, the body displaced, that is 0. So in that condition, work done, that is will be 0, because displacement 0, Fs cos theta. Now another condition, that is when S theta is equal to 90 degree, that is F and S perpendicular to each other. In that condition, if we use this formula, Fs cos 90 0, so this work done gives 0 amount of work done, which is named as no work done. Suppose you are working on a horizontal platform with a load in your hand. So what is the direction of force? What is the direction of force? You are applying force in this direction, that is exactly opposite to the weight of this load. Okay, so the direction of force, that is upward, which is exactly opposite to the load. The weight of the load is directed downward, and your goes like this way, and you are moving along this horizontal road, so this is the displacement, and this is the direction of force. So this angle theta is equal to 90 degree, so here work done is 0. Another condition, in case of circular motion, we already completed. So a body which is moving in this circular motion, what is the displacement? Direction, that is tangential. And what is the acceleration, which is named as centripetal acceleration, that is directed inward. So this is the expression of acceleration, and this is the expression of displacement. So acceleration, that means this also gives the direction of force, that is centripetal force. Centripetal force directed inward, and the displacement tangential. So this angle is 90 degree. So the body which is moving in a circular path, the amount of work done, that is named as 0. So work done is basically 3 types: positive work, negative work, and 0 work. Okay, now another case, you know force and displacement is a vector quantity, so you have to define work done in terms of rectangular component. You have to define work done in vector form. Okay, write it. So Now next part, that is work done in vector form, that is work done in rectangular components. So at first you write force is a vector quantity. So F equal to, you can write Fx I cap plus of Fy j cap plus of Fz k cap, and S displacement is also vector quantity. So here you can write Sx I cap plus Sy j cap plus Sz k cap. What is Fx, Fy and Fz? This is the component of F along x-axis, y-axis and z-axis. Similarly, Sx, Sy and Sz is the component of S along x-axis, y-axis and z-axis. Now you know that is W equal to F dot S. So in the place of F you write Fx I cap plus Fy j cap plus Fz k cap dot, in the place of S you write Sx I cap plus Sy j cap plus Sz k cap. Now simplify. Fx I cap dot Sx I cap. So this one gives Fx Sx I cap dot I cap. Fx I cap dot Sy j cap. You know I dot j, that gives the value of 0. So this value is 0. Fx I cap with Sz k cap, this value will be also 0, that is I dot k 0. So another part that remains, this one Fy j cap, Sy j cap, that is Fy Sy j dot j, and then another part, that is Fz k cap and Sz k cap. So this one will be Fz Sz k dot k, and the remaining combination will be 0 because the dot product of different unit vector is gives the value that is 0. So this value will be Fx Sx I dot I1, this one Fy Sy, and this value gives Fz Sz. So this is the formula, this is the amount of work done in rectangular component. Suppose force F that is equal to given, write 2 I cap plus 3 j cap plus 4 k cap, and S that is given. Okay, you write S not given, the body displaced from this position given 2 3 1 2 4 5 2. Force F vector given, and the given that the body displaced from this point to this point, you have to find out amount of work done. So you know the formula, that is work done equal to F into S. F already given, you have here you have to find out S. S is the displacement. Displacement means final position minus initial position. Here final point given this one and initial point given this one. So final position, suppose this value is named as R2, final position 4 5 2, that is 4 I cap plus 5 j cap plus 2 k cap, and initial position this one, that is R1, suppose 2 I cap plus 3 j cap plus 1 k cap. But here you have to find out S. So S, that is final position R2 minus of initial position R1. So R2, this one 4 I cap minus 2 j cap. So this one will be 2 I cap, sorry 2 I cap. Now 5 j cap minus 3 j cap. So this one will be also 2 j cap. Now 2 j cap minus 2 k cap minus 1 k cap. So this one will be k cap. So this is the value of S vector. So you just use this formula, F dot S, that is 2 I cap plus 3 j cap 4 k cap dot 2 I cap plus 2 j cap plus k cap. Now simplify. 2 2, that is 4. You know the formula, Fx Sx, Fx2 Sx2, that is 2 into 2 4, plus Fy Sy, that is 3 into 2, that is 6, plus Fz Sz, that is 4 into there is 1, so this value is 4. So this value will be 14 units. Okay, so this is the problem, basic problem related to vector concept. Now suppose another problem given. Suppose given F equal to F that is equal to 2x square you have to find out work done when the body displaces x equal to 1 meter to x equal to 3 meter. Now you see here this force, that is F equal to 2x squared, is not a constant force. This force is proportional to x square. That means when the value of x 1, this force will be, you see, 2 into 1 square, that is 2. When the value of x, that is 3, this force value will be 2 into 3 square, that is 9, 9 into 2, that is 18. So the value of force here depends on the value of x. A force is not a constant. So for these types of problem, here you have to use the integration method. You don't use this formula. Okay, you have to use the integration method. And what is the integration method? So our next part, that is, we will solve work done by graphical method. How to find out amount of work done by graphical method when a variable force acting on it. So give the next heading, work done by graphical method. When a variable force acting on it. So at first you draw this diagram. Okay, you draw here force versus displacement. This is the direction of force, and along x-axis is displacement. Variable force acts. So the graph will be like this way. You see, position this one, the value of force this one. Position changes, the value of force this one. So with respect to position, the magnitude value of force changes. So this is the graph of force versus displacement when a variable force acts. So how to find out work done in this case? You consider a small part, very small part, this one at first, small strip. Now you find the area of this strip. What will be the answer? You see, area of strip, suppose this is named as ABCD, that is equal to this is the breadth, that is named as, suppose, dx, and this is the amount of force, suppose this force is named as capital F. So area, that means length into breadth. So this gives F, and this breadth, that is dx. So F into dx, this value gives the area of this small strip. Now you know F into dx, that is F that is force, and dx, that is the displacement, and F into dx, that is named as work done. So here F into del x is named as work done, but this is named as dw because this work done is for this small strip. Okay, so you write that is dw is equal to F into dx. So for finding total work done, you must integrate this part, w, that is equal to integration of dw. Suppose this initial value, this graph from starting from here, initial value x1, and this is the final position, this position suppose x2. So that is integration lower limit x1 to upper limit x2, that is F into dx. So this is the formula which you have to use when a variable force acting on a body. And if W equal to F dot S, this formula you have to use when a constant force acts on a body. And there is another formula for finding work done, that is the area under Fx graph. The area under force displacement graph also gives the amount of work done. You see now, that is area, that is F into dx, this value gives the amount of work done. Okay, so one formula when a constant force, this formula you have to apply when a constant force. this formula you have to apply when a variable force, okay, variable force, and this formula for graphical method, so you have to use these three formulas. Okay, now we will check two numericals related to this variable force acting on a body, how to solve the amount of work done. Okay, check it. First problem, a particle moves along the x-axis from x equal to 0 to 5 meter under the influence of force that value is given 7 minus 2x plus 3x square. You have to find out the work done in the process. So you see here, x0 to x equal to 5 meter, that is the initial limit, and this is the final limit. Force given, you have to find out work done. So the process is here you have to do integration. So what is the formula? Formula, that is W equal to integration lower limit, that is 0, upper limit, that is 5, f dot dx. Now simplify one by one, that is 0 to 5, f, that is 7 minus 2x plus 3x square into dx. Now simplify, that is W equal to 0 to 5, 7 into dx, that is 7 dx, minus again 0 to 5, 2x into dx, that is 2x dx, plus 0 to 5, that is 3x square into dx, 3x square into dx. Okay, now integrate it. 7 constant, so 7 outside, integration dx, you know the integration, that is dx integration x. Integration complete, so there is no integration symbol. Now here limit 0 to 5 minus 2x dx, so here 2 constant, 2 will be outside, and x dx, you know na formula, x to the power n into dx integration formula, that is x to the power n plus 1 divided by n plus 1. So here x dx, so x power, that is 1, so this one will be x to the power 1 plus 1 divided by 1 plus 1, that is x square by 2, that is 0 to 5, plus of 3 constant outside, and this is x square into dx, that is x power 2, so this one will be 2 plus 3, that is x cube divided by 3, x cube divided by 3, and limit you have to use 0 to 5. Now just putting the limit, W equal to 7 in the place of x. First of all you have to use upper limit, that is 5 minus of 0. You take these two outside, so when you take these two outside, these two to cancel out. Here you have to use x square upper limit, that is 5 square, minus then lower limit 0 square, plus of again 3 take outside, so this 3 will be cancel out, and here x cube upper limit 5, so this value will be 5 cube minus of 0 cube. Now simplify, that is W equal to 7 into 5, that is 35, minus 5 square, that is 25, plus 5 cube, that is 5 into 5 into 5, that is 125. So this value 35 minus 25, that is 10, 10 plus 125, so this one will be 135. Unit will be Joule, because force is given in Newton and this value is given in meter. Okay, so these types of problem, here you have to use the integration method. Now graphical problem, this types of problem is important, student. Okay, you see a graph given, force versus displacement graph given. Graph is, that is A, P, P, Q, Q, R, R, B. A body moves from point A to B like this way under the action of force which is varying in magnitude. The value of force's magnitude value is varies, which is shown in this figure. Now here you have to find out the amount of work done, and you know the formula for finding amount of work done. From graph, for finding amount of work done, you have to find out area under this graph. So the total work done here, problem 2, total work done W will be, you see, work done along A to P, so you write work done along A to P, plus of, now work done from P to Q, So W from P to Q. Now work done from Q to R, Q to R, and again work done from R to B. But here you see this is the lower part, this is the positive y-axis, this is the negative y-axis. So this amount of work done, that is gives negative value. So here the total work done will be the summation of this upward value, that is the positive value of work done, minus of this value. So this one will be minus that is R to B, RB. You can write plus also. When we use this length automatically this value gives minus. Okay, now simplify. Work done A to P, that is this value, this area under A to P, that means this separation into this separation, that is 2 minus 1, that is 1, multiple of this separation, you see this value is 10, plus work done along PQ, that is the area under this one. So this one gives the trapezium. So what is the formula for trapezium? Sum of the parallel side half into sum of the parallel side into separation. So sum of the parallel side, that means this value, this side and this side. So half sum of the parallel side, so this side, that is 10, plus this side, that is gives this 15, into separation, that is 3 minus of 2, that is 1. Next, plus work done for QR. You see area under this triangle, QR cover this triangle. So what is the formula for finding area of this triangle? Half into base into height, that is half base, that is 4 minus 3, 1, and height, this is the height, which is gives 15. Now last one, area under RB, that means this area, this also gives the triangle. So same formula, half base, that means 5 minus 1, that is 1, and here you see height, this is the height, and this height gives minus 15. So this value will be minus 15. You can write here negative. When here you use negative, here you have to use this value is magnitude only. But when you use this value is positive, here you have to use this the negative value. Okay, so simplify. You see this value and this value will be cancelled out. Half 1 into 15, and this minus and plus minus half 1 into 15. So the answer will be 10 into 1, 10, plus of this value will be 10 plus 15, that is 25 divided by 2. So 10 plus 12.5, that is 22.5, and the unit will be Joule, because here force unit Newton given and displacement unit meter given. Okay, so basically from graph, when you solve numericals, when you find out work done, you have to do area, you have to find out the area, and the area in the upward portion will be added up and the area in the downward portion will be subtracted. Okay, and when the variable force acting on a body and you have to find out work done, in that condition you have to use integration method, that is W equal to integration F into dx, integration lower limit to upper limit. And when a constant force acting on a body, you have to use the general formula W equal to F dot S. So this is all about the intro class related to work energy power chapter. So here we done work done, the details of work done, unit, dimension, types of work. Then we solve work done, how to find out work done when a constant variable force acting on it, and we solve some basic numericals. Okay, so today I'm ending here. Meet you in next class. Tada.